Picture the ark the way most of us learned it. A wooden boat, two of every animal, a giraffe's neck poking over the rail. That's not what the text says. Genesis gives three numbers: 300 cubits long, 50 wide, 30 high. Numbers precise enough to hand to a naval engineer today. At the common cubit, that's about 450 feet, longer than a football field and a half. So here's the real question. If you take those numbers literally and actually build to them, what happens? Does wood even hold together at that size? I'm Gerald Odom. I've spent years chasing exactly that question, and the answer starts with the closest thing anyone's ever actually built to that length, out of wood alone, in the real world. Didn't end well. That number moves because the cubit itself was never fixed in the ancient world. Estimates run from about 17.5 inches to just over 20. Run 300 cubits through that range, and you land somewhere between 437 and 515 feet. Which cubit you pick changes the ship. The shape matters just as much as the length. Genesis describes a flat-bottomed box, square corners, not a curved hull built to cut water. A sailing ship's curved hull is built for speed and steering. A box like this is built for one job only: staying upright and staying afloat. Different problem, different shape. The material gets one line in the text: gopher wood. Nobody today can say for certain what species that was. The leading guess is cypress, or something close to it, because ancient shipbuilders across the region favored that family of wood. It resists rot in standing water, and it splits into long, straight planks. Wood alone won't keep a hull dry for long, though. Genesis says the ark was covered inside and out with pitch, gopher in Hebrew, a tar-like sealant. It fills every seam a plank leaves behind before water finds it. Bare wood swells and gaps under pressure. Sealed wood doesn't. That's the whole job of a hull, really, keeping the sea on one side of the wall. So has anyone ever actually built a wooden vessel at this scale? Close. In 1909, a shipyard in Bath, Maine launched the Wyoming, a 6-masted schooner 450 feet long and 50 feet at the beam. That's nearly the ark's exact length and width, built in wood by people who knew exactly what they were doing. It didn't handle it well. In heavy seas, her hull flexed. Planks twisted and buckled under the strain. Seawater worked its way into the hold faster than the crew could pump it back out. She sank in a nor'easter off Cape Cod in 1924. At 450 feet in that hull shape, wood had reached its limit. Notice what the Wyoming actually was, though: a curved sailing hull shaped to cut through waves. The ark, on paper, was the opposite. A flat-bottomed box doesn't flex the same way a curved hull does, because the stress runs through the structure differently. Whether that difference is enough to matter isn't something you settle by arguing about it. You test it. In 1992, 9 researchers at Korea's Government Ship Engineering Institute did exactly that. Not as a matter of faith, as a matter of naval architecture. They wanted to know what the ark's proportions would actually do in open water, and they built the test the same way you'd test any hull design headed for production. They built 12 different hull forms, all carrying the same displacement, and compared them on 3 measures: structural safety, resistance to capsizing, and how the vessel handled waves. Then they built physical scale models, 1 to 50, and ran them through the Institute's towing tank under a real wave generator to check the math against actual water. The ark's own proportions, roughly 6 to 1, length to width, came out near the top of all 12 for stability. Not the fastest hull, not the most efficient one, the steadiest. Their model held up against waves as high as 98 feet, about 30 meters, without capsizing. A typical ocean swell in a real storm runs 10 to 20 feet. That gap is large enough to get anyone's attention. So here's what that study is and what it isn't. It's a hydrodynamics result about one hull shape under test conditions. It is not proof the ark was built, and it's not proof the flood happened. A stability number tells you a design could work. It doesn't tell you a history book is accurate. Keep those two claims separate. A stability model on a computer is one kind of test. Building the thing at full size, out of real wood, in real weather, is a much harder one. In 2016, a construction crew in northern Kentucky decided to find out and built it. Answers in Genesis built to the same 300 by 50 by 30 ratio, but chose a slightly longer cubit for the job. The finished structure runs 510 feet long, 85 wide, 51 high. A real design decision on their part, stated plainly, not a hidden one. That makes it the largest timber frame structure on the planet. The build ran about $100 million, close to 5,000 pieces of construction drawings, and roughly 3.3 million board feet of timber. About 100 Amish craftsmen worked the wood using traditional timber framing technique, the same joinery family used for centuries before power tools. Main support timbers ran over 42 inches across, and some pieces, like the rudder, were hand-bent into curved shapes rather than cut straight and forced. One piece of the ancient method didn't survive the trip to today, though. Traditional timber framing joins beams with wooden pegs. Current building code wouldn't allow that at this scale, so the connections here use about 190,000 pounds of custom steel plate across more than 4,000 joints instead. Worth saying plainly, not hiding. Even with modern cranes and power tools, the whole build took just over 2 years. 2 years, with equipment no ancient shipyard ever had. That timeline alone should reframe the next question, and it's got nothing to do with lumber. It's about keeping thousands of living animals fed, watered, and alive for months inside that structure. Feeding and cleaning up after that many animals for months is its own engineering problem, separate from the hull entirely. The exhibit's proposed cages are built from wood beams and poles for the largest animals, wood and bamboo for the smaller ones, stacked in arrays with slotted floors. Those slotted floors and angled trays route waste downward to a single collection point instead of leaving it where it falls. Multiply one animal's mess by thousands, and the design stops being a detail. It becomes the difference between a working system and a disaster. From there, the proposal splits into two systems. Liquid waste drains through a gutter network into a ship-wide reservoir. Solid waste gets shoveled into wheelbarrows and moved out by hand. Neither one is glamorous. Air is the harder problem because you can't pump it in from outside a sealed hull. The proposed answer leans on convection. Cooler surfaces against warm animal bodies create their own airflow, helped by a flue system that could run on a furnace fueled by dried waste. Add it up, and the picture that emerges isn't a boat ride. It's a working farm running nonstop for months. So why run all this math on a story from Genesis at all? Because some of what a text claims is testable on its own terms, separate from the parts that aren't. Proportions, materials, structural math, waste logistics, all of that sits in the same category as any other engineering question. And it can be checked. Whether a global flood happened is a different kind of question entirely, and no towing tank settles that one either way. I'm Gerald Odom. Keeping those two questions separate is what let me take both seriously years ago, and it's still what keeps me coming back to this desk. The measurements are real. What you decide they mean